DAAC, if folks understand that reference from 1970s movie, you can fill in the other words there. Yeah, this is, you know, a big part of NSIDC's catalog in the NSIDC DAAC are passive microwave data sets. I'm going to talk, I didn't put it in the title, but I'm going to focus here just on sea ice for simplicity and being short, not running on too long. But I think next talk might be SMAP, which is soil moisture active passive, a NASA sensor that is also passive microwave, but it has other applicability and has different channels and frequencies. So that's in the plans for the future, probably next. So here we go. All right, so where are we in terms of electromagnetic spectrum in the microwave range? So, you know, visible, you can see the cursor here, you know, here, this is what our eyes see. So we're way over here, longer wavelengths, shorter frequencies, lower frequencies and lower energy. Microwave in terms of Earth remote sensing is generally between about 1 and 100 gigahertz for Earth surface remote sensing, I should say. Atmospheric, they do go above 100 gigahertz. But for sea ice in particular, generally between 1 and 100 gigahertz. And today I'll talk specifically about 19 and 37 gigahertz, or in those ranges. Those are kind of the two main channels that are used for sea ice historically. There are some others that have been used, but for today I'll talk about that.
What does the baseball mean? Like, what are the?
Oh, so that's the size. So this is the wavelength in meters. It's a little fuzzy, I know. And then this is the comparative size. So we're like, yeah, in like the baseball range, kind of centimeters. Yeah. So yeah.
Okay.
Yeah. So yeah, just to give a sense of scale. All right. So this is where we are personally. So we talk about remote sensing. There's two kinds of remote sensing. There's passive remote sensing and active remote sensing. And a passive sensor is just receiving energy emitted or reflected by a source. Our eyes are passive remote sensors, essentially. We're receiving reflected visible light. And so visible light, reflected sunlight, infrared energy, which is emitted by the Earth, basically corresponds to heat and is an indication of the heat of an object or the Earth. And then another one is microwaves, passively emitted. An active sensor provides its own energy. So the sensor is sending out a signal, it's getting a return, and that's how it's measuring it. That's how that signal interacts with the surface and returns back to the sensor, is giving a sense of the and so like radar or synthetic aperture radar, scatterometer, altimeters, laser and radar altimeters, sonar. So, you know, you get pulled over for a speeding ticket, that's an active sensor that is measuring your speed. If it was passive, you probably get away with that. Microwaves, mentioned are low energy. I don't mean that to be too derogatory there, but essentially, when you look at the emission and where the peak emission is for the sun, it's in the visible range, which is how we see. Very high energy. Sun is, you know, a huge energy factory. The Earth absorbs that energy and then emits it in the long waves, absorbs some of that energy in the infrared. And so the Earth is here. This scale is in different wavelengths. We go basically the microwaves up here are just tiny. They don't even show up here. They're essentially almost like the width of that line. So this is, you know, we're looking at really small energy levels in terms of what the Earth emits in the microwave range. So that presents a challenge when we're using microwaves because we need at least one of these three things to really get enough energy. One is a sensor with a large antenna, a big receiver, so that it can collect a lot of that energy. That's not real practical for a satellite. You know, you can only launch a certain size of thing or a certain weight, and also controlling it in space is another thing. You can collect for a long time. If you sit and stare at it for a while, you can get more energy, but of course, a satellite in orbit is not gonna be able to sit there. It's orbiting in low Earth orbit, or you have to collect it over a fairly big area. And in practice, that's what's done, but that means you have a low spatial resolution, you see less detail, you're seeing just a kind of a bulk signal, and it's hiding all the details in there. So that's basically what has been done, is collecting over a wide area, so that's a lower resolution. And then, another thing, this is basically an issue with all remote sensing, but with microwaves as well, everything emits electromagnetic radiation, electromagnetic energy. And so what you're looking at energy from a certain source, like sea ice, but other things are also emitting energy as well, like the atmosphere or clouds and so forth, and those can get in the way. And essentially, depending on the signal and how much of these other sources, your noise, you can kind of block out what you're trying to see. So, then the question is, why would anyone use microwave when I have to use another part of the electromagnetic spectrum? And as I sit here and think about it, I really don't know. That's in my talk, all right? No, there is good reason, especially in the polar regions, like for sea ice. Visible is great when the sun is out, but there's 6 months of darkness in the polar regions, so you can't get data in the winter. Also, there are clouds, and there are a lot of clouds in the polar regions. There's, cloudiness over the sea ice is 70–80% generally. You can go many days without seeing the surface because of clouds with visible light. Infrared, also clouds emit in the infrared, so they're emitting, if there's something underneath, you're not really seeing it, you're seeing the cloud radiation. Another thing is it's measuring temperature, and when you think especially near the ice edge is freezing or melting, it's right near the freezing point. And so the ice is right near the freezing point, the ocean's right near the freezing point, and you're measuring essentially temperatures of where exactly. You have to be very precise in trying to, instrumentation to try to detect that. It can be done, but there's uncertainty with that. But the biggest thing there is clouds. All right, so clouds and visible light. So number one, with microwaves, we're measuring the emission from the Earth. So it's not dependent on sunlight at all. So it doesn't matter if it's day or night, you're just still emitting microwaves. Another thing, I talked about clouds in the atmosphere. In the microwave range, we're here, it's basically what we call an atmospheric window. It means the atmosphere is not absorbing or scattering the energy. The energy from the surface gets to space almost completely. That's kind of the clear atmosphere. There's still the issue with clouds you have to deal with. But fortunately, clouds also do not block microwaves very much. Certain precipitating clouds, heavy like rain clouds, will do that, but you don't get that over sea ice. So for the most part, you can see through clouds with a passive microwave sensor. So that's really great, because now you don't have to worry about daylight, you don't have to worry about clouds, so you can pretty much see the surface. And so this is what you get with a passive microwave sensor. This is the AMSR 2 sensor, this is the JAXA sensor. And this is just from worldview from the same day. And again, you get complete coverage. And so we can get pretty much complete coverage every day, regardless of clouds, regardless of sunlight. And so that's a really nice thing to have. We don't have to worry about gaps in the data, other than a little bit of gap at the pole where the satellite doesn't see the little dark spot there. All right. Another valuable benefit for the passive microwave is that there's been a lot of sensors, and there are still a lot of sensors operating. So we have a long record of data from these sensors. It actually began in 1978 with the scanning multi-channel microwave radiometer, SMMR, or as we call it, SIMR. And then that was replaced by the Defense Meteorological Satellite Program, the U.S. Department of Defense program that launched the Special Sensor Microwave Imager, SSMI. That was succeeded by the SSMIS, Special Sensor Microwave Imager and Sounder. And then along with that, kind of in parallel, JAXA and NASA launched an AMSR sensor, Advanced Microwave Scanning Radiometer, AMSR-E for the Earth Observing System platforms. And then that was followed by AMSR 2. There's a little bit of gap, but those are essentially very similar sensors. It's actually a bigger antenna, so it gets better resolution than the others, but it doesn't have as long of a record. AMSR E started in 2002 through 2011, and then AMSR 2 started in 2012, and is still operating. And we still have 3 of the SSMIS operating. These F numbers, those are the satellite designations, there's satellite numbers, so 16, 17, and 18. And they're also operating, which is really pretty remarkable. F-16 is over 20 years old now, and even the youngest SSMIS and F-18 is over 15 years old now. And so
why the longevity, not so many moving parts? I suspect that's to do with it.
yeah, the missions are planned for generally 3 to 5 years,
Yeah.
but as long as they're operating, it's good. Yeah, the antenna spins. That actually was what caused AMSR E to cease operation. It started the torque on it. It started to gum up the oil or grease or whatever. Lubricant was not working as well. But yeah, it's just passively collecting energy. So it's not, you don't have to worry about a source of energy. I mean, there's obviously battery life and things like that. But once they're up, they tend to last a fair number of years. Now, F-19 I didn't put up here because that went up. And it lasted, I think, 18 months, and then I had some sort of catastrophic failure, I don't remember. So it's not like they all last, but, and that's why they have multiples to have a backup, in case one does fail. So, and then, AMSR 3, which is another JAXA satellite, that is going up soon, I hope. It was supposed to be up by the end of March at the latest, but it did get delayed a bit. And so it's coming soon, is from what I understand. And then there is the weather satellite follow-on, WSF, microwave imager, which is another DoD. Essentially, it's the follow-on from the SSMIS. That was long delayed. So there was this real fear for a while that we were these could fail and we wouldn't have any past microwave data. And our CI structure we'd have to cobble something else together, but we wouldn't have a nice complete CI structure. But we do have the WSF has now been launched. The data is not yet available. It was launched about a year ago. But it should be available at some point and we should be able to get that.
18 and 37.
Yeah. It's actually a little bit bigger antenna as well. It's more similar to AMSR. But it's the same channels, I believe or pretty much the same channel.
Sorry, one other question.
Yeah, no, any
Is
questions?
it like the Chinese Shangri series or something which we can't use?
Yeah, so these are kind of the main sensors that we have used and internationally used. There is, China has the Fenyang FY, yeah, or something like that. They're passive micro sensors, but we don't have ready access to those through NASA and other. There's also some Russian sensors, also limited access in terms of what we as NASA and NASA affiliates can access. So there's also, I've seen some questions about the quality of those data as well. But at least for these, and with the WSF now launched, we have something up there that can take over. And that's important. I'm not gonna go into much, but one of the things, all these satellites are slightly different. And so you want to intercalibrate them. And so you want 2 of them flying at the same time, if at all possible. So then you can compare them and adjust to match the sensors and keep things as consistent as possible. And so there's also, Europeans are putting up a couple sensors. They're kind of standard meteorological satellite program, the META. They're going to have a microwave imager, unfortunately also the same name as the WSF, MWI. That's, I think, 2020, either end of next year in 2026, or it might bleed into 2027. And then the CIMR, Copernicus Imaging Microwave Radiometer, which unfortunately people have started to call SIMR with a soft C, which confuses it with the first one, which is SSMR system. So I always try to call it Timer. I think that's a better name. I'll talk more about that at the end. But yeah.
Oh, sorry.
Yeah, no, go ahead.
Why Department of Defense? Like, what's the defense application?
That's a good question. I don't really know. I mean, the Department of Defense, obviously needs and wants satellite data feed into they run their own weather models, for specific tactical support and so forth. So there is they have, there is some duplication between like NOAA and NASA, and DoD. DoD is on the defense side, NOAA is on the civilian side. They have, these are not the only sensors that are on these satellites, there's other things, and it does feed into their models. And there was the plan at some point to put these all together, what was that called, the NPOs or something, I think it was. And they're gonna like, yeah, but why are we wasting all this, and we're just gonna put them together, NASA, NOAA, and the DoD. And we'll have just one satellite program and everyone, can share, and that was a complete disaster.
Oh, never really happened, never got together.
Now, it turned into the JPSS, the Joint Polar Satellite System. I think that's what that stands for, which is NOAA and NASA. And so they do work, those are both on the civilian side, like VEERS is a JPSS system, or and so, it's a good question. But I think, basically the military has certain needs and they want to control things. Fortunately, the passive microwave is low resolution, it's not like really tactically, so there's no security on it, or they're not real open about the data. But it is available and we can use it, so, so, all right, so we got these satellites out, these sensors, and so we can use the data. And basically, what we're looking for is, what's the energy of the stuff we're looking at, the sea ice or whatever. We can do that with a really complicated, messy equation. It's not really fun to solve, and it's just kind of a pain in the neck and not something that, sane people would really want to deal with. So, fortunately, as far as the data is concerned, we can simplify things quite a bit, and make things a lot easier. Basically, we can simplify it down to just two things: the type of stuff that we have, like snow or ice or grass or whatever, and then the temperature, the physical temperature. The type of stuff is indicated by a parameter called emissivity. It's basically a measure of the emitted energy at a given frequency, of that, it's characteristic of that substance, basically. So this is what's called the Raleigh genes, simple approximation. In the microwave range, you can simplify that kind of more complex equation into basically this, this brightness temperature, which is what we actually measure with the satellite, PV, or brightness temperature. And again, that's an indication of the emissivity and the physical temperature. So things do vary with temperature. A hot object will have a different brightness temperature than a cold object, but it will still have the same emissivity. And so different objects at the same temperature will have different emissivities, different brightness temperature.
But the brightness temperature, you could view it as the equivalent black body.
Yeah,
right.
Yes, same. It's basically the temperature that it would be emitting at if it was a black body. And the emissivity is kind of an indication of the imperfection from a black body. Yeah, thanks. I meant to mention that. Okay, so for the microwave, emissivity is a function of property of the substance being observed, like I talked about. For example, whether water is liquid or frozen. That's kind of nice. Whether the water is saline or fresh. It also is dependent, like I said, on the frequency of the microwave and the polarization, which I'll talk about in a minute. So it's basically what your sensor is sensing, what part of the spectrum it's sensing in. And at some of these frequencies and polarizations, some objects have unique signatures of energy. So you can actually see it like, oh, okay, this is at this frequency with this brightness temperature, this is probably X, like ice. So, everyone thinks sea ice is cool. This is like, right? It's cool, like, yeah. And so, are they right? Well, you look at an image, this is the brightness temperature image, this is 19 gigahertz. And you look at that scale and something's weird, right? So this is temperature or brightness temperature, 280 at the top, 100 Kelvin. So ice is kind of more up in this area here, whereas the water is down here. So sea ice is actually warmer than the ocean in the microwave range, or at least some of the microwave range. So what that means is you've got, obviously ice is colder than the ocean, but it has a lower emissivity, or ice has a higher emissivity than the water. So the emissive properties, the emission of the ice is much higher. So even though the temperature is lower for water, for ice, its emissivity makes it warmer in terms of brightness temperature. All right, so and this I showed here polarization. Backwards. What am I doing? Sorry, going the wrong way. Okay, so I mentioned this is H polarization. So polarization, some substances emit the energy in preferred directions or orientations, depending on the substance. And this is what's called polarization. Instead of just emitting in all directions equally, it has a preferred direction. And polarized sunglasses are, you're familiar with those. Those are kind of a polarizing filter. It basically it allows light only in certain preferred directions, visible light. Yes.
Those glasses that enable colorblind people to see color, do they work similar to sunglasses, or is it totally different?
I think it's different because I think that's measuring the wavelength of the frequency and what gets through. There might be some polarization effect of that, but I think it's probably more the frequency in terms of what waves are allowed through. Yeah, that's an interesting question. So if you like for sunglasses, you allow only certain directions in, cuts down on the glare, and allows you to see more clearly. In terms of microwaves and our sensors, basically we split the energy into specific orientations. It has preferred directions depending on what the substance is. We do what's called horizontal and vertical. It just means they're orthogonal to each other. They're perpendicular. And we just put
I
it.
mean, it's an arbitrary axis, right?
Yeah, it's essentially an arbitrary axis.
Yeah.
Yeah, as long as you're consistent with it. But you're basically you can break down any direction into components.
Right, but it's also saying that there's light coming in and all kinds of polarization,
Right,
but you can break it down to just deal with the vertical and the horizontal
right,
with whatever axis you chose.
right.
Okay.
Right. And for microwaves, it's in all directions, but depending on the substance, will have a preferred direction that it's emitting at.
Right, and
It'll
my
be
understanding
stronger.
for sunglass white glare so bad is that it's in all different directions.
Right. So sunlight is kind of in all directions,
directions, yeah.
whereas the microwave, it has kind of a preferred, or it can have a preferred direction. Yeah. All right, so we look at polarization. On the left is the horizontal polarization. And again, this is just out of the data. So these are in a sense arbitrary, but that's how the data gets processed and split up into these horizontal and vertical polarization channels. And this is again at 19 gigahertz. And so if you look at these, you can still, in both of these, you can still see, right, the sea ice is distinguished from the water. It's warmer. But if you look at the horizontal versus the vertical, the ice is pretty, it doesn't look too much different, but the water looks a lot different. This is much darker, much colder in the horizontal than in the vertical. So water is more polarized than ice. You see this also in the 37 gigahertz, even maybe a little bit more so. In fact, it kind of a little bit hard sometimes. You can see the ice edge there in the vertical. And then if we difference them, then it really shows up. This is the vertical channel, vertical temperature, brightness temperature minus the horizontal brightness temperature. And now it really kind of pops out. And so sea ice is essentially nearly unpolarized. Basically, the horizontal and vertical are roughly the same. But for the ocean, it's much more polarized, and the vertical polarization is much larger than the horizontal. In terms of the brightness temperature, so just emitting stronger in the vertical direction as defined within the data. Okay, so we can put these together, and we can use these various. Oops, I think I skipped this slide here. Oops. I keep doing this. Sorry. Yes. Okay. So sorry about that. we can also look at the frequency difference, right? It's gonna emit differently at different frequencies. So we have the 37 gigahertz and the 19 gigahertz. And it shows up, again, you can see there's quite a bit of difference between the ice cover and the water. There's also a difference between multi-year ice. That's ice that survived through a summer melt season versus first year seasonal ice. So for first year ice, which is kind of a lighter blue, which is around zero, the brightness are about equal. Multi-year ice, the 37, it goes into the negative range, that's this darker blue area. And then the ocean, it's the opposite, the 37 is much larger than the 19. Can anyone guess why the multi-year ice looks different than the first year ice?
So then it's you can beat.
Yes, salinity. So the first year ice, when you freeze the ice, you're freezing salt water in the ocean, and some of the salt gets trapped in the ice. And so the salinity and microwaves are sensitive to salinity. I mentioned that subtly earlier. But after the summer melt season, you've got a lot of meltwater. It flushes a lot of the salt out. So multi-year ice is much less salty than first year ice. So this is one of those hints if you're ever in the field and amongst the sea ice and you're lost and you're thirsty, like don't drink the first year ice, you know, take the multi-year ice, and that will taste a lot better. And so you can kind of see this is the multi-years. Now, this is, you know, just this last March. If I showed you a picture from like 1985, this would all be really dark. Because this used to be all multi-year ice or mostly multi-year ice. So things have really changed. So there's not a whole lot of multi-year ice left to show. Yeah.
And what happens if snow is on it?
So that's a really good question. And I didn't put much in snow to try to keep things simpler, but it's a very important thing. So generally the microwave, if it's dry snow, the microwaves will penetrate through at these frequencies. And so you'll see the sea ice surface. However, when things start melting, which I will talk about, and that's the snow melt as well as like melt ponds and liquid water, that now you've got liquid on top of this ice and that messes things up. So snow is important. And you can have things like recrystallization of the snow and it has some effect, but it's not a huge effect when it's cold and dry. But, yeah, very good question. All right, so put these together. We get like two ratios we can use. Now, one is called the polarization ratio, and that's the polarization of the 19B and the 19H. I showed you the difference there. And then the gradient ratio, which I showed you, the 37 and 19. Now these are ratios, so they're divided by, there's a difference divided by the sum. Anyone have a guess on why one would do it that way?
This is what you call a normalized difference.
It's normalized, yes. So it's basically, these are unitless, as you can see. The key thing, so you see here, you know, it's large for water, small for sea ice, the polarization ratio, negative for multi-year, near zero for first year, and it's largest for water for the gradient ratio. What this gives you, that's really nice, is it makes it independent of temperature. So if you take, you know, this is all brightness temperature, if you like substituted emissivity and the physical temperature for all these, the physical temperature is the same. So that drops out. And so it's just a function of the emissivity, which is a function of the surface and what, you know, your emitting surface, what you're looking at. So it doesn't matter that much if the ocean's warmer or colder. It's giving you this, it's giving you what the water, the liquid water, not the temperature.
So if it was warm, the numerator might be big, but the denominator would be big as well.
Right.
And it would normalize it out.
Yes, yeah. So yeah, this is I call it the Super Ratio Brothers. Not a video game. So if you plot these, this is polarization. You really see, you know, the ice really pops out very strongly in the polarization ratio. You can very clearly see, you know, the dark blue, the low numbers near zero is where there's ice, and the green and yellow is where there's water. And you see some things around here, and I'll talk about these in a minute, these little scattered things. That's atmospheric emission or surface roughening of the ocean waves. And then if you do the gradient ratio, you can see again, the multi-year ice pops out there. You can still, you know, it's not quite as clear and where the ice edge is. this is where it's clear, the ice edge is clear, but they both are giving you some useful information. If you plot those together, you get this, basically, this kind of nice scatter plot. And you see kind of two main clumps, one clump over here on the left, and then one clump over here on the right. And if you actually, look at where these are coming from, basically this over here on the right, that's open water, that's 0% ice. And then on the left over here, that's 100% ice. And then this kind of, the one side is, the top here is first year ice, and then the bottom is multi-year ice. So this is what they call the sea ice triangle. And again, this is basically the NASA team algorithm. You figure out what your brightness temperatures are, you calculate your polarization and gradient ratio, and then you plop it in this here, and hopefully it falls somewhere within the triangle. Generally it does, I mean, there are some ones, there's always noise and some scatter, but basically plop it in here, and you just, wherever it ends up, that's your concentration, along basically the long axis of the triangle, your total concentration, and then on the short axis, the proportion of the multi-year versus the first year. So it's kind of a neat little, it's almost like visual, and again, this was derived by researchers at NASA Goddard way back, starting in the 1970s, early 1980s, and it's completely empirical based. There's nothing, you don't need to know anything about sea ice, you don't need to know what the properties are, really, you don't need to know the salinity, it just comes out of the data. I mean, you do have to understand, like, okay, this is water, this clump is and that, but it's nothing, there's nothing physical that was used in the derivation, it's empirical, just based
Well, a
on
lot
the
of
data.
field validation.
Oh, yeah, so there was a lot of validation, because you do need to know, like, okay, this clump, what does this correspond to? But once you know that, you can go, okay, this is ice, this is water. There is a lot of scatter along here, along the ice, so you don't get a precise center in it, a little bit, and that's basically the atmosphere giving you that noise, because it's not perfectly transparent to the microwaves atmosphere, particularly like clouds, thick clouds, and as well as roughening of the ocean, like I talked about, you get some signal from that. So what's done, again, very simple, is what it's called the weather filter threshold. Just basically say, everything above this line is we're gonna call water, so we don't have to worry about exactly what all those results are. And so it just sets that to 0. Now it does cut off some legitimate ice. It removes a lot of the weather effects, most of the weather effects, but it does remove potentially some ice. And so like a lot of times we use the 15% threshold as the ice, as the definition of the ice edge and the ice extent. One of the reasons is that this weather filter tends to cut off values less than 15%, tends to leave in things greater than 15%. There are other reasons for that too, but that's one of the reasons that you don't go all the way to 0, because you're getting into a lot of noise from the atmosphere. I do want to just briefly mention, that was the NASA team, that was one of the main, NASA algorithms, and we have those data products here. There's another one that was developed also at NASA Goddard called the bootstrap algorithm. It's kind of the same approach in a sense. It's just using different combinations of channels and just plotting different things. And this is kind of the guts of that, is it just plots the 19 vertical versus the 37 vertical, and you get that scatter plot. And again, if you look at validation data and so forth, you realize this cluster here falls along 100% line basically of sea ice, and then this is your 0%, and you again just linearly interpolate between to get your total concentration. There's a weather filter that kind of like, I didn't put that in here, but it kind of cuts off like there. It's kind of instead of a straight flat line, and this is a slope line. But essentially the same thing. It's empirically derived. It's just using different channels. People can argue about which one is better. It depends on the conditions and what you're looking at. But they both have scattered, they're both errors, but they both very clearly delineate ice from water. So getting into some of the issues that we have with that, they talked about the atmospheric emission, the water vapor, liquid water, particularly liquid water is a problem. again, there's the weather filter that removes most of that. We have the low spatial resolution. There's also the ocean emission from wind roughening, which can give you false ice. We eliminate a lot of that with the weather filter, also takes care of a lot of that. We also apply ocean mask. Basically, we apply a mask where it's like, there's not gonna be sea ice off the coast of Florida. We know that, we can assume that. And so we just have mask out areas and say there's no possibility of ice here. So anything that shows up is due to atmosphere or winds. And then NASA Goddard does an additional step that is basically a manual QC where they actually go through and look at each day's data and say, oh, that's an error, that's wrong, we'll cut that out, we'll remove this.
Is that like what the winds, product does?
You mean the brightness temperature product or the?
No, the final sea ice.
Oh, the final sea ice, yes, yeah, so the NASA team and the final sea ice, yeah, that's what they do. Now that's nice in a way because they clean it up, so to speak. But it's also not really open science, it's not, it doesn't meet open data and FAIR principles. We do have the NOAA NSIDC climate data record, which uses those same algorithms, but everything is automated. And everything is traceable and reproducible. So that's an advantage of the CDR, is that it's all tracked. And so, you're not worrying about the subjectivity of who's looking at it. They're expert scientists, they pretty much know what they're looking at. But they also tend to be kind of conservative, they tend to leave things in a lot of times that really are errors, because they want to make sure, especially things along the coast, which is the next thing I was going to talk about, this low spatial resolution. Not only, the low spatial resolution, obviously you can't see details, where the ice edge is exactly, but you also get this artifact of mixed land ocean grid cells, which basically can give you false ice along the coast. Because what happens, these grid cells, like the 19 gigahertz, it's about 69, 70 by 45 kilometers, basically. So it's a big footprint there. And if you've got land there, and in part of that footprint, if you put a grid cell, now this grid cell, you're like, well, that's open water, right? That's 0% ice, it's just open water. But what's going into this grid cell is that footprint, which includes land. And so there's that brightness temperature is gonna be a mixture of the water and the land, particularly during the summertime when the land is snow-free and bare ground. Unfortunately, that bare ground is at a high brightness temperature. The water is a low brightness temperature. And so you put those together and you get kind of something that basically is the brightness temperature of what sea ice is. So you end up with this would show up as sea ice. There's a filter that is applied as various filters, and they kind of go through and go, okay, if it's ice just along the coast and there's nothing else around, it's probably not real ice. And it's automated. It's not perfect, but it at least removes a lot. And then I did mention here, snow. As like I said, is another challenge at times, especially. And that can cause high or low depending on the snow cover, but when it melts, you generally get a low concentration because again, you're detecting liquid water versus frozen water. And if you've got melting snow or melt ponds or liquid water on the surface, that's liquid, and you're getting a signal from that. And so it's seeing it as, well, this is liquid. It's still seeing the frozen ice as well. But it's basically saying, well, this is ice and open water and you get a low concentration, when in reality, it may be 100% or very close to 100% concentration with just some melting water on top of it. So yeah, summer is a particular challenge. This is just a couple examples. Zooming in here. This is, you can see that long line. It has a pretty similar signature to what we see in the ice. It's, it probably technically, if you were just running it through the algorithm, you'd see it as low concentration ice, but the weather filter actually corrects that. You can see that, there's a lot of variability. There's a lot of lower PR values, which indicates lower concentration. When in reality, that's probably completely ice covered or very close to completely ice covered. And then you look like at the coast of Alaska, you see this like it's kind of a blurring out from the coastline where you're seeing this darker lower polarization ratio values that are the same as ice or look like ice. And so if you look at the sea ice concentration field, this is just from the sea ice index, and just grab that, but it's the same day. And you can see, so the weather filter took care of the atmospheric stuff here that was extending out. But it doesn't get all of the land, maybe a little hard to see there, but the yellow circle, there's ice all along the coast of Alaska there, and that's not real ice. It's a challenge because, ice does hang around along the coast a lot of times, even when it's melting, and it tends to grow at the coast first. So when you see ice along the coast, it's hard to say that it's completely false. Now, in some areas, and this is maybe a borderline case almost, because it's, the ice edge hasn't retreated, but if the ice edge is way beyond, you can kind of guess that it's not. But that's one of the reasons it tends to get left in, because they want to make sure they don't pick up real ice, but you do have the potential of leaving in some ice. So, almost ready to wrap up here. Talk about low resolution, right? This is that's the real kind of thing that's the limitation of passive microwave for sea ice and other applications. We can do some things with that. One of the ways to deal with it is build a big antenna. And I said, well, you can't put a big antenna on a satellite, right? Well, actually, you kind of can for microwaves. And it's been done for SMAP, for the soil moisture active passive. It's a mesh antenna that basically unfurls. It's almost like an umbrella kind of thing. And it's not a solid antenna, it's a mesh. And so it can unfurl to a big size, you can pack it in, it's lightweight. But it gives you the effect of a big antenna. It's actually 6 meters antenna, whereas the SSMIS antenna is about 1.5 meters. And the AMSR is about 2 meters. So it's 3 times, at least 3 times as big as anything. And so that gives you much bigger resolution. Now SMAP is at a low frequency, 1.4 gigahertz, and it actually can be used for sea ice. It's really good at seeing thin sea ice, but it's not really great at seeing like your overall big sea ice areas. And it was designed for soil moisture in particular. It's very good at soil moisture at that. And at the low frequency, the lower the frequency, the bigger the footprint tends to be. So 1.4 gigahertz with like a 2 meter antenna, you get just huge area. It really wouldn't be very useful. So that's where the mesh antenna comes in. Then there's also the CIMR, Chimer or Simmer, that's due to launch, I think, in 2029. And this is kind of neat because this is also going to be about a 6 meter mesh antenna, but it's not going to be 1.4 gigahertz. It's going to be like the 19 and 37 gigahertz. I think it does still have 1.4 gigahertz on it, but it will have these higher frequency channels, and that will give us upwards of 1 kilometer resolution from passive microwave, which is really pretty amazing to be able to do that. So that's going to be really useful when that is launched. The other way to get higher resolution, which some folks around here are quite familiar with, is to do some fancy signal processing. The individual footprints are these big footprints, but they overlap. They're taking measurements, along the scan lines and along the orbit, and then multiple orbits cross over. So you're getting many looks, and especially in the high latitudes, like where sea ice is, you're getting a lot of looks, a lot of footprints from the same place at close to the same time. And what you can do is you can take those footprints and how they are oriented in the geometry and the signal of those, and basically synthesize a higher resolution by looking at those. The way we've done it in the past, and it's typically done, is you just average all the footprints into one grid cell, and you just get that average signal, and so you've got a 25 kilometer. But if you actually use the individual footprints and how they interact with each other and how they overlap, you can synthesize with some fancy signal processing that's called RSIR, which is synthetic image reconstruction, I believe. Well, I think it was scatterometer image reconstruction originally, with the R being for radiometer. So this was developed originally by David Long at Brigham Young University, and then worked with Mary Jo Brodziak here, as well as Molly Hardman, to basically do this. It was really done for scatterometer, but then to do it for the passive microwave. And so it was originally a measures project, which is basically a NASA funded program to make these long-term records. It basically takes the 25 kilometer to is high resolution is 3.125 kilometer. The actual improvement's about 30 to 50%, but still it's pretty significant. So that was completed several years ago now, and then it was transitioned to the DAAC. The DAAC decided agreed to take it over, and that turned into the product NSIDC 0630, which is currently in its reprocessing phase for version 2, which is adding some new brightness switchers and adding Amser 2 specifically. And then we'll be doing near real-time updates. There hasn't been, this is all just brightness temperatures, but we've looked at some of the potential for sea ice products from other projects, and you know, there's a lot of potential. This is just one, it doesn't show up great on the screen here. But this is the enhanced resolution versus the standard resolution from Amser 2. And again, it may be a little hard to see, it shows up better on the computer screen, but you can actually make out like individual flows there, and you can see a lot more detail than you can see in the standard resolution. It's very pixelated and much better in the enhanced resolution. So there's a lot of potential for this for sea ice. It's being used already for snow cover. Recapping, you know, the plasma microwave is big advantage because it's all sky conditions, day and night, through clouds, in most clouds anyways, and it's continuous and consistent multi-decadal record. So we've got 47 years of data. That's one of the longest satellite climate records that there is, really. And then, yeah, the limitation is the low spatial resolution, land ocean mixing. The summer melt is challenging. We use extent because that's basically a total area covered by a certain threshold, 15%. It's pretty good even under melt conditions. It's saying, well, there's ocean or there's ice here, but exactly the concentration is where it becomes challenging and the errors get high. So that's why we use extent, which is just anywhere it's above 15%. And you can get weather contamination. There have been several algorithms developed. I showed the NASA team and the bootstrap. Those are the two main ones that we've had here at NSIDC, but there are other ones, and they all have their pluses and minuses. They generally agree, at least in terms of like the trends and variability. And then there's a lot of potential. People have started looking at like AI methods to better classify the ice and process things. Fusion, if you add visible imagery where there's not clouds, and then use the plasma microwave where there is clouds, you know, you can take advantage of at least better image, better resolution in some places. And yeah, I think this is basically the last one. So this is the products. We have, you know, a ton of products at sea ice from plasma microwave, either brightness temperature products or sea ice products. The first three are the brightness temperatures. We have the simmer and the SSMIS and SSMI. That's kind of that's NSIDC 0001, our very first product, the OG product. And then we've got the sea ice concentrations, the NASA team, and the bootstrap, and then the CDR somewhat more recently. But these are all long-term, designed to be long-term consistent climate products. So they're kind of our bread and butter sea ice products. And then we have the Amser products, brightness temperatures and sea ice, which are newer. We also have those. And I focus here exclusively on sea ice concentration, but you can also look at melt onset. Like I said, it's very sensitive, whether it's liquid or frozen, so you can actually detect when the melt starts. We have a product for that. And we can also track the motion of the ice and keep track of it over time to look at the age. So we have products for that as well. So I think with that, that's it.